Hello, we're back. This is the final set of formula you need to learn. This set of formula allow us to calculate the pH of equivalence point, or otherwise we term it is the pH of the salt solution. You will find that in any neutralization, you realize that by looking at the pH graph, as more and more, say for example, ethanoic acid is added to sodium hydroxide, the pH will start coming down at this point here. All right, this is when actually all the NaOH inside the conical flask is completely neutralized. So this point here is termed as our equivalence point. So equivalence point is actually a point where all the acid and all the base completely neutralize each other. Whatever is left behind is only the salt. So as evident in this equation, so this is the only salt that's left behind. So the salt will undergo hydrolysis to form two ions. Obviously, in the case of Na+, you just have ion dipole with water molecule, so it does not affect the pH. But if CH3COO- is the only species that's present in the solution, that is obviously a weak base. And hence, CH3COO- can perform the role of being a proton acceptor and actually produces these two species here. And we can then put up a Kb expression as such. And in the same vein, if one of these decides to ionize, we produce one of ethanoic acid and one of OH-, which means these two numbers are always equal. Hence, it will be concentration of OH- squared. All right. So this is the expression that we will use to calculate the pH of equivalence point of a salt that is produced from a weak acid. So as we understand, if a weak acid is neutralized completely, it will form the salt, and the salt would actually be a alkaline salt. All right. So Kb equal to con OH- divided by the concentration of the salt. Okay. So there's actually another way that we could calculate that using Kw over Ka. How does this come about? Let's take a look by looking at this box. So taking a look at the acid, ethanoic acid, and if it was given with acid dissociation constants like Ka, all right, we could have a Ka expression as such. So this is just merely an equation where the weak acid dissociates. If you look at this expression for Ka and this expression for Kb, which is the Kb expression for its conjugate base, in this case specifically CH3COO-, if this Kb and this Ka multiply together, you can see the CH3COO-, which is actually at the top, will cancel off the CH3COO-, which is at the bottom for this expression. Similarly, in the case for the ethanoic acid, they will cancel each other. So by taking Ka and Kb and multiply together, you will only be left with con H plus multiplied by con OH-, which means that it's equal to your Kw. And this is from this expression itself, we can now actually manipulate that and make Kb equal to Kw over Ka. So in a nutshell, this is the formula that you use to calculate the pH of an alkaline salt and solution, and the salt is produced from actually a weak acid. All right. Okay, let's now take a look at the calculations for the F1 acidic salt that's produced from actually a weak base. So for example, ammonia, all right, that is used to react with HCl inside the conical flask. And at the pH, at the equivalence point, all right, the pH will be less than 7 because the salt that is produced is actually your ammonium chloride. Ammonium chloride will actually ionize to form NH4 plus and Cl minus. And again, Cl minus will not be involved because it will just merely have ion dipole with water molecules. NH4 plus, if exists alone, is actually a proton donor, so it's a weak acid. So you could actually ionize to form this expression, and this is when we can have a Ka for it. H3 plus divided by the this will be your salt. Okay. And in the same way, if one of these decide to ionize, you will produce one ammonia and one H3 plus, 3O plus, so these two are equal. Okay, so this will be a salt. So this will be the formula you could use to calculate the pH of your acidic salt. In the same way, if we are given the Kb, all right, of ammonia, then you'll find that we can write the ammonia undergoing ionization to this OH minus, and the Kb expression is as such. And in the same way, you could see that the if we take Ka multiplied by Kb, all right, the NH4 plus, one is on top, one is below. The NH3, one is below, one is on top. So if they multiply together, you will also end up with OH minus multiplying with the concentration of H plus. All right. So that is actually your Kw, which allow us to conclude that Ka is equal to Kw over Kb. All right. So this is a formula that we use to calculate the pH of an acidic salt that's produced from actually a weak base. And be mindful that when you use Ka, Kb equal Kw, they are only to be used meant for either the Ka of the weak acid and Kb of its conjugate base, or the Kb of the weak base and the Ka of its conjugate acid. All right. So only when you multiply both that I've described, then that will be equal to Kw.